Alright folks, before we get started on piecewise functions, or the introductory part to piecewise functions, you're going to need to have this piecewise functions. This is in the 6.2 folder in a individual folder labeled piecewise functions. So we're looking at a real world example of what a piecewise function can be used by. So the Freewheelers Bicycle Club went on a Saturday bicycle trip. The graph shows the relationship between the time in hours and distance in miles from the starting point for one female club member. She traveled away from her starting point in a straight line. When the timing started, she was already traveling at the given rate. Use the graph of D and the table to answer the following questions. So, we've got the graph of the distance. We also have a t-chart over here, a variable called t and a variable called d. The first thing it's going to ask us to do is try to figure out, for this situation, blank is a function of blank. When we say is a function of, we can also say is dependent on. So right now, go back through both your paragraph up here and look at your other this stuff and figure out what is this D representing, what is this T representing in our real world context, and then write this solution in. Alright, if you need to pause it, pause it. Okay, now we're back. Part 2. Write the labels on the appropriate axes with the unit. So remember, this axes is just plural of axis. So what they're saying is, hey, make sure you write one of these axes is going to be one thing, one of these axes is going to be the other thing, and then also make sure you say it's measured in miles. So when you put your whatever it is on there, so put it's either looks like time or distance. So put either time or distance, and then if your unit is miles for your distance, then put miles. And the same thing over here, and just put it in parentheses to say this is measured in units, and this is measured in units. Part 3. During which interval is she moving the fastest? So, when we say moving, we're looking for a speed. I mean, that's what the fastest means, is a speed. And I always remember speed as like a miles per hour. Right? So like cars, driving a car. So when we say miles per hour, that's really saying speed is miles is a measure of distance divided by the hour, which is a measure of time. So figure out for each of these three pieces, which is why we call this a piecewise, it's not the same thing all the way across, for which of these three pieces is she moving the fastest? Part 4 is a little bit of interpretation. Describe what is happening on the bicycle trip for the first 2 hours. And that's up to you. Okay, part 5. The graph consists of 3 distinct line segments. So we've got our 0 to 2 interval, we've got our 2 to 4 interval, we've got our 4 to 7 interval. Write an equation for each part. One for the interval t equals 0 hours to t equals 2. One for t equals 2 to t equals 4, and one for t equals 4 to t equals 7 hours. This graph is called a piecewise function and would be written as this thing. So we're going to go into our book of parent functions right here, and we're going to try to figure out which of these functions that this kind of represents. So they say that it's line segments, which means it's linear. So what we have is ordinarily a linear function goes through 0, 0, and this is our vertex, right? So 0, 0. So for us to figure out each of these, we need to make sure that we remember all the stuff from our linear equations. So from earlier on in the year, and it's been a long, long time ago, we can say that we have the slope of the function minus h and then plus k. And this minus h and plus k are the same as we did in 5.5 and 5.6 and 5.7. So they've already done the first one for us. So it looks like what they found is that during the first interval from 0, so during the first interval from 0 is less than or equal to t is less than or equal to 2, our equation is 15t, because it looks like the slope, we've got a rise of 30, so that's 30 divided by 2 hours. So 30 divided by 2 is going to give us that 15 for our 0 is less than t, which looks like over here, this is our domain, and just the domain from 6.1. So domain from 6.1. Okay, so let's see if we can figure out the equations for each of these. So it looks like for this one, if our origin always starts at 0, 0, according to our parent function thing, we're going to move right 2 and up 30, which is going to be, okay, so right is minus 2, and then up 30 is plus 30, and that will get us to this point here, You can use any point you want to, so you can use this one or this one or this one. After you simplify, you'll get the same thing. If we look at our slope, we know horizontal slope, we have no extra distance, or we have no change in y, so we have 0 divided by 2, which is just 0. So after we simplify, this is going to give 0 times all this stuff is 0, which 0 plus 30 is just 30. That says the equation for this part is just 30. There's even no t because it canceled out. 0 times anything gets rid of it. And we also need to say for our interval from 2 to 4. So that says from 2 is less than or equal to t is less than or equal to 4. And the last one is for the interval of t equals 4 to t equals 7 hours. So right now, we'll do the same thing. If you would please, figure out your slope, figure out your shift right, and your shift up. I think we should probably use the same point. So I'm just going to use the closest one to the origin. We're just going to use the point 4, 30. So do a shift right of 4 and a shift up of 30, and figure out that slope for that last thing. All right, pause it, and then get back to me just to make sure that you're right. Okay, so for that equation, we're going to have a rise of 30 units and a run of 3 units, which says we have a slope of 10. We're going to use right 4 and up 30. So when we distribute, we're going to have 10x minus 40. So 10x minus 40 plus 30, which we can simplify. Oh, we shouldn't be using x, we should be using t, because that's what they have up here. Sorry about that. Let's use t instead. So then negative 40 plus 30 is negative 10, so we're going to have 10t minus 10. And there's the whole equation written. We know that our interval is from 4 is less than or equal to t is less than or equal to 7, just like the other guys over here. Okay, let's put the back side. Part 6, when is d equal to 22 miles? Show the work that leads you to conclusion and interpret the meaning of the answer. So here's the thing that we've got to do to make sure this happens. One, we've got 3 equations up there. So we've got, on the front side, we've got 3 equations. We've got to determine which equation we're using. So pause the video, flip over to the other side, figure out which equation where we're going to have our input of 22 miles. And again, if you haven't paused it, go ahead and pause it. Okay, so here's what I'm looking at. If I know that my left axis is distance, my right axis is, my x-axis is time, my y-axis is distance. I know I said right, it's up and down, it's weird. 22 miles is right about here, which says it's somewhere in this range. So it looks like to me that if we're looking to figure out at what time exactly, it's somewhere between 1 and 2 hours. But we need to be precise about this. So we're going to use our equation for this piece of the graph, which the equation is d equals 15t for this segment of the graph. We can ignore the rest of it. We're only looking at this part. So I'm going to copy this down. So d equals 15t. We also then we're going to figure out, we're going to find t by using d equals 22, just like it says right here. So we're substituting in 22 for d equals 15t. If you would please go ahead and solve this on your own, and you can give me the decimal answer or the other answer. I really don't care, it doesn't matter. I prefer fractions, but that's fine. Alright, go ahead and solve it and then pause it while you're solving it, and then we'll move on. Okay, so this is 15 times t. So to undo both sides, let's divide by 15. So say t equals, you can even say 22/15ths, which you can approximate decimal. I don't know if that is off the top of my head, but you can plug it in the calculator. 22 divided by 15, and that's fine. This is an exact answer. So at the time when we're 22/15ths of an hour is exactly when she's 22 miles. Oh wait, number 7. What's the average speed for the interval t equals 1 hour to t equals 3 hours? So when we're looking at an average, we actually dealt with averages. We deal with them on a pretty frequent basis. But remember, you average something by adding all of the individual terms up, all of each, and then you divide by the number of things that you add up. So divide by the number of things. So if we're looking for the average speed, I need you to add all the speeds and then divide by the number of speeds from t equals 1 hour to t equals 3 hours. So we flip on the other side. we've got t equals 1 to t equals 3. That says we've got two chunks. We've got a speed from 1 to 2, and we've got a speed from 2 to 3. So make sure that you find your speed, add them up, and then divide by 2. That's how we find an average. Okay, pause this, do this now, and get back to me. Alright, my average speed was 15 for the first interval, 0 for the second interval. There's two of them, so I'm going to divide by 2, which gives me 7.5 miles per hour as an average speed. Okay, so at the end of the fourth hour, the bicyclist decides to go back to her starting position. Illustrate what the graph might look like for the return trip. So I'm just going to copy over just a rough sketch of the graph on the front page. We've got our time along the bottom. We also have our speed along the sides. So 1, 2, 3, 4, 5, 6, 7. Now let's just put another in there. 10, 20, 30, 40, 50, 60, 70, 80. We said this was distance in miles, and this was time in hours. I also know that my first line segment goes from 0, 0 to 230, so I'm just going to put a point there and connect those to make a line segment, and then we're not moving for a little bit from 2 to 4, staying at 30 miles an hour, so I'm just trying to keep this as horizontal as possible. It looks like that instead of keep going up like that happened, the bicyclist decides to go back to her starting position. Well, here's the thing you got to think about as you illustrate this last part, and this is going to go different for everybody, and that's okay. Two things to think about in my opinion. One, you can't go backwards in time. You can only go forwards. So the graph shouldn't have a line that goes backwards to her starting position, because not only are you going backwards by going down, but you're also going backwards in time. So the other thing you think about, part 2, is the speed involved. So think about her speed in here. Think about how the fact that she's done this for a while, she might be tired. Create a realistic decrease so that she can go back to her starting position, which is at y equals 0, somewhere on the x-axis. And then after you finish that, part 9 says create a story for the original graph of the function d for the interval t equals 0 hours to t equals 7 hours. Okay, alright guys, so this is all we have for our first introduction part. I'll be getting some practice sheets out for you, so come ask me about the practice and then we'll get started.